And I'm very pleased that we're going to have another very well-known invited keynote speaker in the area of subspace clustering. He is Dr. Akram Aldroubi from Vanderbilt University. He's a professor of mathematics at Vanderbilt. I was thinking what to tell about Akram. First, he's one of the most brilliant persons that I have ever met. I can say that. He's one of the most intelligent people. How do I know? In fact, in 2007, I decided to go deep in mathematics. Actually, I'm a computer science faculty. And I decided to pursue second PhD. And I look at Vanderbilt, and I saw Akram, and his area was exactly matching to my area. We communicated on Starbucks, and I still remember that conversation. And I said, that's the person I can work with. And we started finding an area that can be a bridge between computer science and mathematics. And I'm sure from the talk so far, you can see that subspace clustering and high-dimensional data analysis is a bridge area between engineering and computer science and mathematics. So, and then after we checked the papers in that area from Dr. Vidal and others, we said that's the area to work with. And since 2008, I've been working with him, and we are enjoying it. We are doing it for fun, basically. And again, he is a professor of mathematics at Vanderbilt University, and he is a fellow of the American Mathematical Society. And he has authored and co-authored more than 100 articles in the various areas of harmonic analysis and its applications. And he is editor-in-chief or co-editor-in-chief of Journal of, can you tell me? Yeah, so one of the major journals in sampling theory. So, and I'm very pleased that he is here. I asked him to give a talk, not very mathematical, not very technical, so it's just in between, so that he emphasized what subspace clustering is and what are the state of the art in this area, so that we have been hearing about it since this morning. So by the end of today, hopefully everybody will have some ideas and maybe some interest in that area. With that, please help me in welcoming Dr. Aldroubi to the stage.
Okay, can you hear me? Well, thank you very much, Ali. This is the nice thing, actually, of having students that are very good. They go out, they do very well, they say very nice things about you, and they invite you to give a talk. But actually, Ali, it was really more of a colleague and a friend than a student, and we work together rather than a professional student professor relationship. So I will be talking a little bit about subspace clustering and its application. Like Ali said, that it will be not too mathematical, not too application, so that means nobody will understand anything. Right? So now I'll try to make it clear, and please stop me anytime there is something that's not clear, and I'll try to explain that. So I really enjoyed all these talks this morning, and I hope I can do half as well. Okay, so what is the subspace? I'm going to talk again about the subspace segmentation problem, what it means. So the subspace segmentation problem is basically you are given a set that consists of a union of L subspaces. So you've seen this is subspaces of some Hilbert space. That Hilbert space could be infinite dimension, could be finite dimension, could be Rn, could be some Hilbert space. So, and a vector space with an inner product. And you're also given a certain number of observations that are actually drawn from this union of subspaces. And so this is a set of observations. And what you want to, from this set of observation, what you would like to do is to determine everything. In fact, let me just do it. In some sense, we need to go back. We need to determine these subspaces, their number, their dimension, and actually find a basis for these subspaces, only by looking at the data. So that we know the data come from a set of subspaces. It's a union of subspaces, but that's all we have. And we want to be able to determine the set, in particular, to determine these union subspaces. So that is, I think, have been presented several times today. And this is, in some sense, when L is 1, that means when you have a set of data, and you know they come from a single subspace. This is a very well-known problem. This is essentially you try to find a flat that is closest to a set of data, right? So this is a very well-known problem. And of course, the fact that you have possibly more than one makes things a little bit more complicated. Makes it more linear. Makes it, how do we do that? So this is the basic problem. And let me give you just a very simple toy problem. So suppose in fact, here those are affine. They're not even subspace. So those are two union of affine spaces. And the green and the red points here are essentially points that are drawn from these subspaces. Now, of course, the red here and the green here seem to be mixed. All I'm saying here is that you have this collection. And if you pick one, if you separate this collection of points into two bins, you're not sure which belongs to subspace. So you get the mixture of points that belong to this affine space and other. So the question is, can you first separate the points correctly? And once you separate them, perhaps it should be easy also to find the subspaces in some fashion. So this is the typical problem. So motivation. So where does this problem comes from, and why is it interesting? So you have seen René Vidal this morning talk about computer vision, motion tracking in videos. Several of you also have shown this face recognition problem. So to track motion or several objects moving in a video, and I'll talk more about it, essentially turned out to be a problem of finding a union of subspaces from a set of points that are observed. Again, face recognition is the same problem. I will not talk about that. So these problems have already been around for quite a while, and here are some of the people that have contributed to this area. Now there's another problem, which is signal processing or signal modeling. So many of you have worked on signal processing, and you may have thought, okay, well, band-limited functions is a very good model for signals, and it is. But why people chose signal model for band-limited function for signal model? Band-limited functions, for those who do not know, those are functions such that their Fourier transform is 0 outside a certain compact set, say outside -1/2 or -3t. So they don't have high frequency. So the reason why this model was good originally was because for many applications, this is what we have. When we hear radio, we can't hear above 20 kilohertz. When we see images, there are certain frequencies we don't see, of course. And therefore, a model like called the band-limit model is a good one, but then there are other ones for other purposes, and they all share one specific idea that they are invariant under. If you take a function in the model and you shift it, it's still in the model. So those are called shift invariant model. To determine a shift invariant model, which is not necessarily band limited, is another problem, or one or several union of such shift invariant space This comes up in more recent signal processing modeling. And in fact, one of the people that started these type of models here, Yulu, with Martin Betterly, and has done beautiful work and very inspiring work. Compressed sensing, so many of you have heard about compressed sensing. So we say, okay, a signal is sparse. What does it mean? It have few non-zero components. But in what basis? In what frames? Right? You have to know that. Otherwise, you can't really do very much. So when you talk about compressed sensing, you're talking underlying the compressed sensing is a model, a finite dimensional model, in which in a particular base, signals or class of signals is sparse. You change the base, they're not sparse at all. Right? They don't have to be. So it is important to know sparse in what basis. So what basis means you need to choose a model. What dictionary? Possibly it's sparse in a frame, not necessarily, or an overcomplete. Stop. Okay, overcomplete situation. Now, some of you in this morning also have talked about learning theory in some sense, and a little, right? As we talked about this morning about, anyway, trying to find the intrinsic dimension of certain low-dimensional subspace and high-dimensional data. And there is a way also to connect to connect the union of subspace model to the learning theory of low-dimensional spaces in high-dimensional data by doing what is called the flat transform, which I'm not going to go into, but it's very much related to the union subspace problem. So all these are reasons why this type of problem came up. And of course, in general, so again, this is the toy problem. So you have, say, a union of three subspaces from which data is drawn. And this is the data that is drawn, which means in this toy picture, I'm saying that the data is not perfect. The data is noisy. The data has, so the data are these points there. The data is noisy. Some of it is a total outlier. So I have three subspaces, two two-dimensional and one line in white here. And so we need to deal with that as well in general. So things are never perfect. I guess this is, I just said it. You have corruption by noise. You have outliers. You have missing data points. And it seems like this is a difficult problem that some of you have addressed and some of you talked to me about this morning. So let me tell you a little bit about the structure of the talk. So I will start by talking about existence of solution to the subspace clustering problem. So this is the mathematician. You know, one day they asked a mathematician and an engineer and a physicist, what is the square root of 4? So the engineer came out in a second and he said, well, look, it's 2. I can do it directly on my calculator. The physicist came out and said, well, after an hour, said, well, it's a number between 1 and 3. And the mathematician wouldn't come out. And finally, after 2 days, he comes out and said, square root of 4 exists. So it may be not, so I'll talk about existence. And then signal models, I'll talk a little bit about signal models. So again, it's more of a problem. How can we actually find the signal model from a set of finite set of data or signals? Then I'll talk a little bit about computer vision or motion tracking. I just talked about a couple aspects. There are many other aspects. Just to give you an idea about what has been done, you already had several talks about it. And so it will be another time where we emphasize maybe perhaps a couple other methods. Anyway, so existence of solutions. So let me now talk a little bit more about the mathematical problem. So what is the mathematical problem? you have data, it's corrupted by noise. So it is drawn from a union of subspace, perhaps the subspace are finite dimension, perhaps it's infinite dimension. The one thing that we can do is to try to solve this problem is to find to reduce it to finding a minimizer to a cost function, right? So we want a certain number of flats that are as close as possible in some sense to the data. So we're given a set of data. Here they are. These are observed. Again, in some Hilbert space and some finite or infinite dimensional vector space. And we want to find a sequence. Maybe here I'm assuming that we know that there are L subspaces. And these L subspaces, each one of them belong to a certain class of subspaces. So class, it can be anything. Finite, infinite, bizarre looking, it doesn't matter. So we have a class. This is where we search for L subspaces that belong to this class. Each one belongs to this class, such that this functional is minimized. And I'll explain a little bit what this functional is. But basically, you pick a function, you fix L subspace in this class, you fix them, and for each observed function here, you compare it to each fixed subspace, and you see which one is the closest to this function. That's this minimum. You use among this fixed configuration a space which is as close as to f1. And then you compute this distance. And then you do the same thing for the second vector, f2. You look at all this fixed configuration. And again, you compute the minimal distance. And after you do that, you compute the minimal distance of all this set to this fixed configuration. And that's give you a number. Now you let all these spaces take all possible value or configuration in the set script C, and you find the minimum or all these possibilities. So that's what we want to find. But does it exist at all? Is there even a way of finding it? So here is a possible class. If you are in, say, Rn, n dimension, the class of C could be, for example, the set of all subspaces of that dimension R, or less than or equal to R fixed, and R is some number less than n. That could be an example of such a class. But this is a very simple class. I mean, you can have much more complicated class. All right, so this is the problem set again. So you take this cost function, and you want to find the minimum of this cost function over vi, for example, if I choose this class, such that the dimension of these guys is less than or equal to R. That would be for this problem in which H is Rn and C would be this. So that is the story problem. And here is an example of what I'm trying to say again. Suppose I have just 3 points, and in R2, and I want to find 2 subspaces that are as close as possible from these 3 points. So what do? I fixed these 2 lines, and for this fixed 2 lines, I look f1 is closest to v2, so I compute this distance. f2 and f3 are closest to v1, so I compute these distances to v1, and this is a number. Then I change the configuration from this v1 to v2, v1 like that. Now suddenly f1 and f2 are closer to here, so I compute the distance of f1 and f2 to v2, and then f3 is closest to v1, so I compute, and now I can compare these two and decide to take the one that's smaller, but of course now I take all the possible configuration, and I should be able, hopefully, to find a minimum if it exists. In this case, of course, it exists, and we all know that, because this is a very typical problem that we know how to solve for at least 100 years. Is that okay? Any question?
Yes.
Yeah.
Go back.
Yeah.
So that existence is based on a fixed L.
Yeah, this one, in this particular problem, I fix L, but I let the class completely arbitrary, and I fix actually this 2. It's a distance squared. So I want to just look even at this problem.
Right, because if L is M, then that distance is 0.
Of course.
Right.
Of course.
So what you want to do is characterize for each L between 1, which will be the entire plane, all the way to M.
Right. So, right. So you're absolutely right. So I'm given a set. Let me put it a little bit slightly different. Suppose I know that I have data that is drawn from L subspaces. Then it wouldn't make sense to have M equal to L data, because I will not. And I mean that's so. Normally M is much larger than L to start with. So you're absolutely right. That's yeah.
Also, why wouldn't the minimum exist?
I'll show you. Because I can give you many examples in which, almost trivial, in which the minimum does not exist. But I will characterize completely the case. I'll tell you exactly when it does, when it doesn't. And it's not totally trivial. Now, it may not be important in practice. I don't know. But I can tell you there are many, many cases in which it doesn't exist.
It doesn't have to be 0.
No. It just doesn't exist.
Okay.
It just is not there.
All right.
So basically, there is an amphimum, but you never reach it. So for example, I mean, the typical example would be, suppose I have an open interval, just 1, 2. 1 is not included, 2 is not included. So the amphimum of all the numbers between in that set exists. It's 1, but 1 is not never attained. So I really want to find an attainable solution.
Yeah, I'm just
in my set.
I'm just curious what kind of geometry would induce such.
Yeah, I can. Very good question. But I can give you examples, simple examples. And in fact, it turned out that it's really it's kind of it's a very complicated problem, even in this very simple case. But we'll talk a little bit more about that. Any other question? Okay, so well, the first thing that I want to characterize for this particular, and of course there are other cost functions that you may want to characterize things, but this is the one we looked at because this is one that we have seen that people were trying. We did it. We tried to also minimize things over. This is essentially the mean square. So this is least square type. It's not quite least square. It's a over nonlinear set. But anyway. So you want to minimize this functional, and you have a class C. So, and those subspaces belong to this class C. This class C again can be very general. Whatever each point in this class C is a subspace of is a subspace. It is in general an infinite uncountable set C. So C is a class of subspace of H, and every VI is an element of C. So to actually respond to this problem, to say something about the existence, you want to give C certain topologies. I mean, metric. You want to talk about how close things are. And you want to be able to talk about, when we talk about trying to find a minimizer, you want to be able to talk about like this. Often you want the set to be closed, for example. In any case, you need to think of VI as points in a space, and you want to give the space a topology to be able to talk about things. So how do you do that? So those are flat subspaces. You think of them as operator. You think of them as projector, because every space, you can think of it as the either the range or of an orthogonal projection. Right? So you can think of V. You forget about V. You say, okay, each V is a projector. Is an orthogonal projector. So that's how you start thinking about these spaces. So each V in Ci is an orthogonal projector. And then since projectors are operators, so they are functions if you want, then there are already well-known topologies on these. Topology, is to be able to talk about closeness and how things are close, how things are far in some sense. And it turns out that the right topology to think of the set C's when we think of the subspace as operators is the weak topology. And I don't want to talk about that. There are all kinds of topology you can put. There is one that is very natural. It's called the weak topology on operators. And this is the one that is the right topology here for us to solve this problem. Finally, what we need, I'm going to show a theorem that completely characterizes, tell you exactly when and when you don't. We need to talk about not C, but something that we add to C. And I'll explain a little bit what that would be. We'll be talking about C plus. Actually, this should be superscript, C plus. And what C superscript plus is C, and you add to this C all the positive operators. So we're thinking of the class C as a set of projectors, and C plus is a set of these projectors plus all the positive operators. And we take a topology on that. And then the result tells you, at least in the finite dimension, and then I'll tell maybe a little bit more about infinite dimension. So when H is a finite dimensional space that have dimension D, these three conditions are equivalent. And let me, before I go to this and tell you what this is, tell you, step back a little bit and go to calculus 1 and think about, we have a function and it's continuous on a closed interval. So we know it has a minimum and a maximum, and it stays at 10. Okay, so here, if I knew that, in fact, we know that if under this topology and the way we are describing subspaces now as points, and if C was closed and compact, means like similar to closed interval, then we certainly will be able to find a solution. But you can also prove that you can find solutions. It doesn't have to be closed and compact. In fact, if this C plus was closed, then you have a solution. And if you have a solution, then this has to be closed. So this is the equivalence between the two. This is an if and only if statement between 1 and 3. It's also an if and only if statement between 1 and 2. What this says is that the convex hull, for those of you who know, I'm not going to explain that. If you don't know, it doesn't matter. The convex hull of C plus, whatever this thing, must be equal to the convex hull of C plus closure. If this holds, then it's also equivalent to having a solution. Having a solution is equivalent to that. So this completely characterized. So you give me a C, I'll be able to tell you whether you have a solution just by checking this. Yes?
So what if the solution is actually one of the positive operators? So that
one of the which operators?
So we have the class C, that is the class that we like, right? But then for some reasons that we didn't talk about, we need to add some positive operators.
No, that's right. So
class, right? So what I'm saying is that I see.
Right. So the solution is in C. The characterization is in C plus. So just to give you an idea, C could have what you want a solution in C.
Yes, sir.
Right? But you get it, but the condition is not on C. It's on C plus.
And by the way, what are the positive operators?
What are the positive operators?
I'm sorry, I really have bad hearing. But yeah.
So what is a positive operator on a Hilbert space?
Oh, okay, so the positive operator is self-adjoint operators such that if you, in this case, where in finite dimensions, just a self-adjoint operator that have all its eigenvalue are non-negative. Okay, for infinite dimensionals, a bit more complicated, but it's essentially similar to that. So this is a specific characterization of existence of solution in any class C for finite dimension. In infinite dimension, things get a little bit more hairy and a bit more complicated, but we have also theorems about the infinite dimensional case. In particular, actually, this is not the right even this is not quite the right characterization. Usually you have this implies that in infinite dimension, but you cannot go backward. You have to do something else, and you have a different characterization. But that's all I want to say, is in general, things are not necessarily, you give yourself a class doesn't mean that you have a solution. Okay. So next now I'm going to pass to my second topic, which is signal modeling. So here, the problem is we have, again, a union of subspaces, but each subspace is infinite dimension. Now I talked about finite dimension. So now we're talking about, normally signal modeling involve infinite dimensional space. So we have a union of infinite dimensional space, but those spaces are not arbitrary infinite dimensional space in L2, for example, but they are actually shift invariant, which means if something belongs to such a space, its shifts also belong to such a space, and those are called shift invariant space. So in most applications for signal modeling, what you have is that you have a union of shift invariant space. What are these? So I will tell you what are these. So what is a shift invariant space and how do you construct it? So one way of talking about shift invariant space is you take n functions and you shift these functions on a grid. Let's say ZD. Okay? So Z. You shift them on the integer. Let's say you shift those on the integer. So you shift, let's say in fact you take one function for the moment, n equal to 1, and you shift this one function on all possible position in the integer. And then you take, now you have a bunch of functions. The function has all the shifts. You take span, you take linear combination of this function and all its shifts, and then you take a closure in, say, L2. What it means is, well, you make this space complete, and that would be a shift invariant space. Now, some shift invariant space kind of generated by a single function that you shift and you take linear combination of the shifts and you close, and some of them involve more than one generator. You take 2 or 3 or n functions, you shift them on the grid, you take finite linear combination, you close that, and this is a shift invariant space. So for those of you who are familiar with a band-limited function, every band-limited function is a shift invariant space. And what is the function that generates the band-limited function of shift invariant space? Is the sine pi x over pi x. That's what it is. So that's a very special case of such spaces. So now the problem then that we are interested in is you're given a set of observation data, f1 to fm, m images, for example, and you want to find a union of L subspaces of this form, which have, for example, n generator. So for this, I'm going to introduce this notation. You take the set of all shift invariant spaces that have n or less generators, actually, and you call that script v sub n. So this is every element here is an infinite dimensional subspace of L2, and it's of this form, and it has at most n generators. And there is incomparably many of those. So band-limited function is one of these, one example that belongs to this class. So the problem now is you're given a set of functions, m, so those are signals, those are images, those are whatever you have. They belong to L2. And the question is, can you find a subspace or a union subspace? But in fact, let's make it even simple. Can we find, suppose L is 1. I'm looking for a single subspace V that is best approximate this set of data. In finite dimension, we know this problem is very easy. I have a bunch of data in Rn. I want to find a single plane that is close to this data. This is the SVD. We know how to do that, right? So this is the simplest problem of the union subspace problem, except that in infinite dimension, things get a little bit hairy. And moreover, here you have finite data, but every subspace that that belongs is an infinite dimensional. But then you should ask, well, if I have m data and I have an infinite dimensional subspace, it's trivial. I should be able to just find a zero distance from an infinite dimensional space. This is data. So why is that not the problem? Why is this not correct, what I'm just saying? So this subspace have a structure. They are actually, even though they're infinite dimensional, they have a they are very structured. They are shift invariant space. So this is like not any any subspace of L2, but those have also structures. They are shift invariant. And therefore, there is absolutely no reason, if I have m finitely many data, that I can find subspace that match them exactly, as long as I'm looking for subspace that belong to shift invariant space of n generated. So, look. That's exactly the trick. Exactly. So because of the shift of this structure, you can go into okay, so first of all, let me tell you what this is, and I forgot the weights there, but it doesn't matter. You can minimize this. You can find the subspace. Now I'm looking at one subspace, V shift invariant, which actually is best fit in this set of data. And the way to do it is exactly what Yulu just suggested. So, well, I can diagonalize this problem in some sense by taking the Fourier transform. When you took the Fourier transform, the problem becomes an uncountably many, actually this is where the trick is, uncountably many finite dimensional problem. So you solve these problems by your usual trick that you know how to do. But then you have to put things together in the right way. You have to prove things. You can put them in a measurable way to actually find the correct solution. So it's an application of the Fourier domain, of a little bit of measure theory, and of the Eckhart-Young theorem. Okay? And because we rely on some well-known technique in finite dimension and the Fourier transform and some other things, then we can actually, given a set of data, we can actually estimate the error very precisely. So not only can we find one, but there is a way of finding the error that we make in a nice way. And this was a solution to a single problem, but we can use this to actually prove that, in fact, we can, once we are able to find a single solution to this problem, a subspace problem, we can use part 1 and 2, and it's not a big step from there. So this is all I want to say.
Is there any connection between these results and the previous one in the sense of
Yes. Yes. It's a very good question. So the question is, the compactness result that I had shown before was for finite dimension, but there is one for infinite dimension that we had I didn't show. And we could have proven this result that there exists such a solution without knowing how to obtain it, using actually the result about existence. But the way things happen, actually, we first started by working on problems like this. So, and we found how to do it, and then we thought, well, what if it was a more general problem? And but you're right. So this, the existence of such solution is subsumed by a theorem from the existence. But you don't know how to do it. Well, here we have an exact method. Yeah.
And I don't know if it's done later, but you have promised to give us a counterexample.
I will do it maybe on the blackboard, but it's a very easy counterexample. Remind me, it's a very easy counterexample. So let me tell you a little bit now about video motion, and already many speakers this morning have talked about that, but I will just want to, doesn't hurt to do it again. This is actually a picture that I stole from Ali, right, Ali? And so think of this as an object. So this work actually, some of what I will do, this is something that Ali and I did a few years back. And this is why I'm allowed to steal this, right? So so think of an object that is moving around. It's a solid object. And this is the camera plane. And you have a point. And this point is moving because this object is moving around. And so the camera sees the projection of this point. And this point here have an x1, y1 coordinate of that point P. And then as next frame, you get an x2, y2 of the same point P, etc., and goes on. And so you have, let's say you have n frame in the video. You get x1 of P, y1 of P, and to xn of P, yn of P. And you put you string all the xy component of the projection in one big vector, and then this vector belongs to R2n, where n is the number of frames. So that's what you do. And it turns out, so for this object, each vector that you have in R2n is a very, very long vector. If you have 1,000,000 frames, this is R2 million, so vector that has 2 million components. Now you take a different point, and you have another 2 million components. And you can take a third point, but it turns out that no matter how many points you take, you can prove actually that all these vectors that are taken from different points of the same object that is moving around, that they span a subspace of dimension less than or equal to 4. And this you can prove simply because the object is solid and you take the center of mass and you move things around. So this you can prove. I mean, this is nothing difficult. That's why it is. Okay, so then if we have several objects that are moving around in a video, one way of trying to separate the motion would be to take points from one, to take points from the other. Maybe we don't know which point belongs to which object, but we have points from the videos, and then to try to put to cluster these points into different cluster, each one belong to an object. So that is that, and it turns out that this is a subspace clustering problem, and here is a right. So how do we do that? Okay, so you can see in this image, you have various things, geometric figures that move around, and this is actually from the Hopkins data set. And in red, these are points that you track. You make these long vectors that I told you about, and you put like vectors. These W1 is possibly a vector from here. W2 possibly a vector in blue. From the blue, we don't know which is which, but we put all the vectors in a big matrix W, and this matrix have very, very long columns. And this is the data set that we obtained from, say, a video. So because of what I told you, to each moving object, they are associated a subspace of dimension less than or equal to 4. The question is, how do we take this matrix, separate the data into clusters, each one belong to a single object? And Renee talked beautifully this morning about this problem, so I don't want to go too much more than that about this. I'll just talk about a few methods. And René Vidal talked about the sparsing method this morning, and then he also talked about some of the contributors, and Candace lately have also contributed to this problem. Algebraic method, that's again one that has been started by Vidal a long time ago, and it's called the general principal component analysis algebraic method that he presented this morning. There are other methods which are variational methods and K-subspace method, etc., and other statistical methods that people have done. But I will talk about methods that are today. Actually, Ali suggested that I add something. So there is one point that I didn't add here. He wanted me to talk about something we had done together. And so just as he was introducing me, I was trying to finish what he thought. So anyway, so today I'm going to be talking about this method. This method combined with something else, and other ideas that will be coming now. So let's see. A method that called the reduced row echelon form, and this is a really nice way of telling you what the problem is and how there are in some sense, some simple way of doing it, but it doesn't necessarily work very well. Anyway, so suppose I have a set of data, and I have capital N of it, and they come from a union of subspace. Now, for some reason, the subspace I'll sub-I. But anyway, they come from a union of subspaces. And so, and each vector here has dimension capital D. And I don't know how many subspaces there is, so this is not known. But suppose we all have done Gaussian elimination, right? So you have AX equal to B. One way of solving it, you just do Gaussian elimination, right? And you do something called the row echelon form. And when you do Gaussian elimination or the row echelon form, and you take the reduced row echelon form, you usually get, if the problem is invertible AX equal to B, you get the identity on one side and then the inverse on the other side. And so we're going to do the same thing here. This is not this is a rectangular matrix. This is not a square matrix. But why not do just Gaussian elimination on this matrix? And suppose after we do Gaussian elimination, we actually get something that looks like this: identity one, an identity matrix, another identity matrix, another identity matrix, and then. So this is kind of a bunch of identity matrices, and we have zeros perhaps here, and then we have stuff there. In fact, we can always do that in principle. If things are not noisy and if the subspaces are independent, let's put it that way. So if that's the case, if we can do that, then I claim that then the problem is immediately solved. We know that my original data here, all these columns that correspond to this identity and these columns here correspond to one subspace. All these columns here that correspond to the second identity, and this will be another subspace. So everything I'll be able to read directly from this matrix, if I could do that. And it turns out that I can always do that under the condition I told you. And essentially, you don't get quite a matrix like that, but you get this up to a permutation, and therefore you can still read exactly, you can separate and cluster the thing. That is under no noise, under nothing at all. So if the data is generic, here's an example. So we actually took vectors like this. We made a W, which corresponds to a certain number of subspaces. I don't even remember how. So you look at this, and you have no clue what is going on, of course. But then you do this reduced row echelon form, and immediately you can read what column here belong to the same cluster, and what is the dimension of subspace, and how many subspaces there are. And I just did this. We just did here Gaussian elimination essentially, and everything in red belong to the same subspace. So that means first and third, and this, which correspond to 6 and 7, and I don't know, the 11 and 12 belong, all those correspond to the same subspace. The corresponding column here to these blue things correspond to the same subspace, etc. So you can read everything, but that's assuming some things, of course, including that there are no noise. So what if my matrix had noise? That things that we picked were from subspace, from unit subspace, but there are noise. So when I do my reduced echelon form, I don't get these zeros that you had before in the matrix before. I get some small numbers possibly. So you see, when I said, if I draw data from a unit subspace and I do my row echelon form, reduced row echelon, I should get things like that. There is a lot of zeros and everything. But if there are noise, unfortunately, the structure doesn't appear anymore. But there are things here that are non-zero. So is there a way to kind of do a thresholding and get rid of these and still do the clustering? So can we find a good threshold? And the question is, what is a good threshold? What does the threshold depend on, etc.? So it turns out that the threshold depends on many things. But most importantly, it depends on the angle between the subspaces. And you can give an estimate on essentially what the threshold should be in terms of the minimum eigen, the minimum singular value of A, which is essentially bounded by the angles, and have an idea about how big the threshold is and whether your method is going to work. And I'm not going to go too much into detail, but here is a theorem that essentially tells you more or less whether you can do it, how well it will be, and we tried this method, and it turns out that at least for the stuff that we tried it on, and typically the 155 Hopkins data, it does not work very well. And I think René Vidal just pointed it out this morning, the angles are actually small. So this is not you don't expect things to be working. But if you know somehow that the angles are not too small, this method should work relatively well. And certainly should work relatively well if relatively well if so for an initial stage of another method, for example, an iterative method. Okay? But there are many questions. For example, is there a way of modifying? Because this method, the reduced echelon form, is a really simple, nice, fast idea. So it should be, if there is any way of modifying it and making it robust to noise, even when you have little small angles, it will be great. But we haven't been able to do that.
But you can compute the reduced echelon form. But then there is another step, which is how you go from that to a segmentation. And presumably, one could convert the reduced echelon form to continuum.
Yeah, absolutely.
And then get a much better segmentation.
This is correct. And we have done that, I believe. And we still weren't too happy about the result. But I think we got slightly better results.
The reason I argue that is because the reduced echelon form is somewhat similar to that method of Gear.
That's correct.
And at the same year that the Gear paper appeared, the paper of Canale appeared.
Mm-hmm.
And neither of them use spectral clustering. But with the modern techniques, you just take those.
We did use spectral clustering on this, and for the data that you have on the Hopkins, and it wasn't too satisfactory for us.
How did you convert this into a That's a critical step.
That's correct. So I don't remember how we did. Do you remember, Ali? We did something or probably. I guess I don't really remember. But we weren't satisfied on that data. So for the data we have, it didn't work very well.
Question?
Yeah.
So there was a talk earlier which was talking about the shape interaction matrix.
Mm-hmm.
And basically was saying that if we have the matrix W,
Mm-hmm.
then compute the SVD.
Mm-hmm.
and then which is U sigma V transpose, and then take V times V transpose. So I have the impression that
They're connected.
that they're
Definitely
connected, right?
They're connected. Yes. They're connected. This is, as far as I know, we proved two things. The reduced relational form, like René Vidal pointed out, actually is, in some sense, is that what he did? Maybe not, but in some sense, in fact, it is a reduced echelon form he does, but he doesn't prove anything, and it was on a very special case. So this, what we did in that particular work, we proved it in general. When does it work? When does it work? And then we just showed the theorem about how well it works in terms of so that's our contribution to this problem. But you're right. So this V transpose is connected. It's not exactly 100%, but it's connected. You're right. You're absolutely right. So finally, let me talk about, do I have time or? Almost done, okay. 10 more minutes, no problem. There is another method that is related to many other methods, which Ali and I, because we were not satisfied finally with this particular beautiful mathematics, but not enough good results for the particular motion tracking, we decided to look at some other things. And we used various things that are known, some ideas from spectral clustering, some other ideas from local, I think, finding the subspace by looking locally at the neighborhood of points, etc. So I will talk a little bit about this just to give you an idea about what we did. And because these ideas are the same essentially everywhere. This is not so much, there are many ideas that are more or less can be applied in other situations. The first thing that you should do, you have this huge matrix of data that have, say, columns M rows and N columns. But M could be very, very large. But in fact, your matrix in general, its rank is low. So N could be 1 million, N could be 5 million, but the rank of this matrix could be 4, 12, 20. So you don't need all the matrix. You need, in fact, to cut it down. So the first thing you do, you make a dimensionality reduction. Now, there are many ways of doing it. Singular value decomposition and take only certain row of the matrix, etc. The question is, if you do this dimensionality reduction, you want this new matrix, which is much smaller in row, to have the same cluster as this. So that's a question, right? But you do that. And you do that in the right way. And this new matrix that have this column data, but many fewer rows, all rows. In fact, the rows are, say you are looking for L subspaces of dimension d each, then the number of rows should be roughly L times d. Much, much smaller than N in general. So the first thing you do in general is a dimensional reduction if you want to find a union subspace from a set of data like the one actually. Then you normalize. So there were a lot of talk this morning that, well, you have these subspaces and the points are in these planes or in these hyperplanes that are very far away. And you can't compare them. When you want to take a local neighborhood and see points that cluster around, there is a problem because things are on a plane that could be very far away. But there is one remedy, a very simple remedy, and you should do right away. You take all your points in that plane and you normalize. Now, normalize and you put it on a sphere. And now many of the points that were far away are not far away anymore. They belong to the same space. They belong to a sphere and intersection with the subspace. Moreover, you could do more actually. For example, you could take, you can in fact do a little bit better than that. But now taking a neighborhood or points that are close to a certain point or vector, that now have been normalized here is not too bad. So, in fact, after you normalize, you put everything on the sphere, you can use, you don't have to use, but one method is to use a local, you're going to use, pick every vector in here, and look, if you know that your subspace of dimension D, look at neighborhoods that allow you to construct, look at several points that are near xi that allow you to construct a subspace of dimension D. That is a d-dimensional local subspace. And it consists of xi and a certain number of neighbors of x. So once you have, so for now you can construct a huge matrix, and this is the affinity matrix that René Vidal thought about. You want to, it's an n by n matrix. Remember, we started with first an m times n. We reduced the thing to r times n, and then suddenly we're back to an n by n. It could be a huge matrix. But it's an affinity matrix. It's kind of is trying to compare now every point with every other point. So x1 is as close to x1 as possible. But x2, is it close to x1? How is it close to x1? We use the fact that two points are close if their local subspace is close. That's one way of looking at it. And so we construct this affinity matrix or similarity matrix. So we have a big matrix and that consists of ones and zeros. And 1 means so if x1 and x3 are similar, we'll put a 1. If x1 and x3 are not similar, we'll put a 0. And there is a way of doing that. That's how we do our affinity matrix. And from this, we transform, by doing this, you transform a problem into a slightly simpler problem and a more doable problem. So again, you have this affinity matrix, S, that you construct. And essentially, you have reduced your original problem, which is finding L subspace of dimension D, to finding, by doing this, all I've shown you before, finding L subspace of dimension only 1. In the perfect case, of course, things are not quite that, but that's what essentially is trying to be done. And to finally solve this problem, because still we have an n by n matrix, but it has only rank L, we can reduce this by using singular value decomposition into n time L row times n columns, and then use a very simple off-the-shelf k-mean clustering algorithm. And this is essentially the one way of solving this problem. It turned out that doing such a problem, solving this problem this way is at least for this type of moving object, seems like it does very, very well. And we tried our algorithm on this. And let me give you, at the time, what we had. Things have changed. And in fact, let me see, the GPCA was the first one, I guess, that René Vidal had done. And he said that this one wasn't working very well. And you can see in this test on the data set of motions, there are many methods that are compared. In this particular one, the GPCA was not doing too well, but it seems like the new version that he's working with the students seemed to do much better, and it's maybe around here or better. But let me just tell you about the results here. So this is the different techniques, and those are essentially percent error, the percent of misclassification of a point that belongs to subspace, but you put it in the wrong space. So GPCA for two motions are doing okay, but it's still 6%. Then you go a little bit, and this is the one that René Vidal developed a few years ago, which was the sparse spectral clustering. And here you see it's almost perfect. Our method seemed to do slightly better at than that. This is for 3 motion. And again, you can see roughly that this method that I showed you last seemed to be doing very well. The really other method that essentially are the same is the sparse spectral clustering, and this is also 3 motion. So that's all I want to say. I have a review of many techniques and methods that you can have. It's everybody can get, from this website. It's free. So it's a review on the subspace clustering. It's from my point of view. So there are many others. It's perhaps emphasize more some of the mathematics and some of the applications, but you can certainly, what I talked about today is in there, and that's it. Thank you.
Great talk. And do we have any questions for couple?
What I noticed since yesterday is that in most of the talk, we talk about union of subspaces. And usually in stochastic analysis, people use sigma Hill or sigma algebra generated by subspaces of interest. And I wonder why, is it because in this case, why we, instead of taking that kind of approach, is it because sometimes the space generated by those subspaces may just give you the whole space that we have or not? For example, in 3 dimensions, if you take a plane and a line, if the line is not in the plane, the smallest subspace containing both might just be the whole 3-dimensional space.
Right.
Is that the problem? Is that the reason not to?
Right. So the reason why I think is that we do not want to find. So first of all, we could find for given data, say a single subspace that best approximates this data, but sometimes we want to finer details, right? And if the data, like I think this example was given just before, and let's say you're in R3 and your data come from 2, well, certainly you can pass a plane, but it's too coarse. You want to get a little bit better than that if you can, and if it's the right model. So this is why, in this case, if you want to model by a single subspace, well, then that's 2-dimensional, but you may want really a union of 2 finer subspace, and then that's really a union. I'm not sure if this is what your question was about or it's something else.
Yeah, because the fact that you are talking about some percentage of data that are not in the right place, for example. And if we were to bring everything in one space,
Right.
we will not resolve that issue of thinking that, okay, the classification is a percent of data that are not properly classified due to, let's say, the location is the distance from the data to where they are actually is not the right. It's small, but then they are not in the space where they are supposed to be.
That's right.
So the question I'm asking, if we were to consider by let's say smallest subspace containing both spaces, would that not address the issue?
Well, it addresses the issue, but you don't get. You're absolutely right. But then you pointed out, if you have a subspace of dimension 2 and one of dimension 1, and you have noisy, and you try to find the one that, in fact, will have 0 error, but it will be everything, and it's not as good a model as being finer. So you want to kind of refine your model. Let me go back. I think René Vidal also asked me what is a simple problem in which you have a solution, but so first of all, that you don't have a solution is very easy, right? So to not have a solution, I'll give you an example where you don't have a solution, but the infimum exists. Very simple. That's just very simple. Because you can think of C as all one-dimensional line in R2, except, of course, this is a kind of concocted example, but still, everything except everything except this x-axis. Now suppose there is no reason for me not to take the points that are actually coming from the x-axis, right? So certainly, the closest I come to this, to the angle 0, the closer but the infimum doesn't exist. So this is a very trivial example of I picked the wrong class to find a solution. Now, let me give you another example. So the reason for this in this particular case is that C actually is not closed in the weak operator topology. But I can give you okay. So let me give you an example. Suppose I give you the following example. I give you so let me take the set C to be the set of all. So I take a 45-degree. I'm not sure if this is drawn correctly, but so this is a plane, and it's 45 degrees from the x and the y axis. And then I take all lines, C to consist of all lines that are in that plane, one-dimensional line, plus, except for maybe this, okay? So now I'm going to make the other example, except this, so it's kind of similar to this example. But now I'm going to add to these lines, plus the plane xy. So this is the xy plane. So this is not closed either as a class. But even if I take stuff right around here, I can find a minimizer. I can't, it's not going to be this line because this line is not, but it's going to be the plane. So this is where you have this characterization in which, okay, does it exist? Well, okay, if it's closed, it exists, but so this is where the C plus, if you want. You have these little holes, so you can actually make it a little bit better than C plus, but well, anyway, so that's all I want to say. So that's maybe address your question. Yeah.
Thank you very much.